Okay, so we're going to continue along the vein of looking at Hamiltonian systems and their associated first integrals. And of course, one very, very important example of such a system is given by Kepler's problem, which describes a two-body interaction between two massive particles where they're interacting under the mutual gravity. Okay, so this is the two-body problem. Evolving under mutual gravitational interaction. Okay, and for simplicity, I'm going to again rescale some of the variables so that's scaled out. So mass of the first particle is equal to the mass of the second particle is equal to 1, and the gravity is equal to 1. Okay, the way we're going to set up the coordinates is we're going to fix the center of the coordinate system at the first body. Okay, and then choose a two-dimensional coordinate system where Q is equal to Q1 and Q2, which are the components of the position variable, okay, for the second body. So what basically you have then is that you have Q1 and Q2. This is M1 is the position of the first particle, and that's assumed to be the origin of this coordinate system, and then this is M2. Okay. So with respect to that choice of coordinates, then you can write down a Hamiltonian. Okay, so you have a Hamiltonian which depends on these two components of position of the second particle as well as their corresponding momentum, P1 and P2. And the Hamiltonian in this case is of the form kinetic plus potential energy. So this is 1/2 P1 squared plus P2 squared. Okay, then there's a potential energy term, which is -1 over square root of Q1 squared plus Q2 squared. So this is a 1 over R kind of potential term. Okay, so if you have that Hamiltonian, it's like then as before, you can substitute this into Hamilton's equations. And what you get is that Q1 dot is equal to P1, Q2 dot is equal to P2, and then P1 dot is equal to minus Q over Q1 squared plus Q2 squared to the 3 over 2th power, and then P2 dot is equal to, sorry, minus Q1, okay, minus and minus Q2, Q1 squared plus Q2 squared to the 3 over 2th power as before. Okay. All right, and as was the case with the pendulum, it's possible to eliminate the momentum variables to then write this in a system of second-order differential equations just in the position variables. Okay, so you could write this as Q1 double dot is equal to minus Q1 Q1 squared plus Q2 squared to the 3 over 2th power, and then Q2 double dot is equal to minus Q2 q1 squared plus q2 squared to the 3 over 2 power. Okay, so you can write this in the following way as well. Okay, so associated with this Hamiltonian system are two first integrals. As we saw before, the energy is, or the Hamiltonian more precisely, is always the first integral of a Hamiltonian system so long as the Hamiltonian doesn't have explicit time dependence. Okay, and then there's a second first integral here, which is the angular momentum. And more generally speaking, what we will see is that oftentimes with Lagrangian and Hamiltonian systems, there is an intimate relationship between conserved quantities or first integrals and symmetries of the problem. Okay, so let me just sort of say that the way the Hamiltonian is expressed, it's easy to convince yourself that if you were to rotate the positions and the momenta in the appropriate way, then this Hamiltonian stays invariant. Okay, so what that more or less means is that the Hamiltonian is invariant under rotations. More precisely, it's invariant under what is called the cotangent lift of the rotation action. But in any case, it's what happens is that the physics is somehow independent of the choice of coordinate frame. So there is, if you will, there's an arbitrariness. It's like to how you choose to, prescribe. It's like this sort of orthogonal frame, and the physics is invariant with respect to that. And a consequence of this rotational invariance then is that there's an associated conserved quantity, which turns out to be the angular momentum. So we'll see how that goes in a little bit. Okay. So the other thing it's like which is preserved is the linear momentum. So so there's the linear. I guess I should have said it's like what some of the first integrals are. So the first integrals include the Hamiltonian, and as well as the angular momentum. So let's look at how you go about doing this, but in a slightly more general setting. Okay, so so we're going to look at the we've already studied the case for the Hamiltonian. It's like, so let's look at the momentum cases. So let's look at linear and angular momentum. For the n-body problem. Okay, so if you have a system of n interacting particles, which are interacting pairwise, okay, you can describe this as follows. Okay, so let's write down the Hamiltonian, which depends on Q and P here. Okay, and so so now it's like I'm changing the notation. So now it's like you should think of the QIs. It's like as corresponding. It's like to the position vector, if you will. It's like of the ith particle. Okay, so here QI is the position vector of the ith particle. So this is in contrast to the formulation we had before. It's like when we were talking about Kepler problem, where Q1 and Q2 were the components, if you will, the position of the second body. So now it's like notationally, it's like the Qi is the position vector of the ith particle. Okay, so if you have that, then it's like the Hamiltonian looks like the following. You have a term involving the sum of the kinetic energies. Okay. So this is going to be of form 1 over mi, pi transpose pi. Okay, so the same way that qi is a vector, it's like pi is also going to be a vector here. And then you have the, so that's the kinetic energy term, right? And then you have a term which involves a mutual potential. Okay, so we have the sum over all pairwise interactions. So I equals 2 to n, sum from j equals 1 to n minus 1. Sorry, I minus 1. Okay. And then you have a potential term which I denote by Vij, and it depends only on the pairwise distance. It's like between Vi, Qi and Qj. Okay. Okay. All right. So then you can check that with a Hamiltonian like this, that there are two first integrals. Well, actually, there are three in it. The Hamiltonian is, of course, again a first integral, but there are two momentum first integrals. So one can check that the linear momentum which has the form the sum of the pi's, right, and angular momentum, which is of the form the sum I equals 1 to n of Qi cross product pi, right, our first integrals of the flow. Okay. All right. And again, it's like what we're going to see later is that these conservation properties, these first integrals, are a special case of Noether's theorem. In Noether's theorem, it's like it's a general result which relates symmetries of the Hamiltonian with conservation laws of the system. Okay, so later we will see that these are related to translational and rotational invariance of the system via what is called Noether's theorem. Okay. All right. Okay, so let's stop here for now.